My name is Aidan, and I represent Marvin Tillman, Armand Lewis, and myself, and our hypothesis. We're experimenting on the marshmallow death in the microwave, and one of our hypotheses says that marshmallows that are narrower and taller will survive longer in the microwave than shorter and wider marshmallows. In other words, marshmallows that survive longer have a smaller radius but a greater height, and the ones that survive shorter have a greater radius and a smaller height, as you can see right here.
Please explain.
I already did. And then the next thing is that our goal is to find the instantaneous rate of change in terms of volume per second that the marshmallow is in the microwave, because as the marshmallow is in the microwave, it's going to lose height and gain radius. And how much the volume changed is what we're going to be determining.
And I was asking about explaining, I meant like, could you show them the pictures of the smaller one? And yeah, just explain that.
Yes, definitely. This is how the taller and narrower one starts off. And
right.
This is how the shorter and wider marshmallow starts.
Right.
As you see, this is similar to that, and this is similar to that. And then after a certain point, it finally gives up, and then it dies in the microwave at 20 seconds for a shorter and wider, and 30 seconds for taller and narrower.
Right. So this is pretty much everything?
Well, we also determined a hypothesis for marshmallows that are in proportion to one another, and we've determined that a very tiny marshmallow compared to a large one there is going to die faster because of less of a volume.
Right.
Because something that has less of a volume has less room to expand, and whenever it has less room to expand, is likely to die quicker.
All right. Thank you for your time. I just want to determine your hypothesis for such an excellent project, and hopefully it goes well.
Okay. Today, myself and my partners, Armand Lewis and Marvin Tillman, came to a conclusion of what the derivative of the volume is for the bigger marshmallow. The volume derivative equation is, as you see up at the top, 2 pi r times r derivative in parentheses, and you multiply that by height, plus pi r squared times the derivative of height. We knew that the height, the original one of course, of the big marshmallow was 5 centimeters, and the 5 centimeters was measured on our video as being in 8 pixels, and when we created a positive slope between a certain point, we discovered that the slope was 1.93. So we multiplied 5 times 1.93, as you see there, and then we came to 9.65, which equaled 8x, as in the way you do proportions. We divided 9.65 by 8, and we came to x equals 1.2, so the derivative of the height is 1.2. For the radius of the big marshmallow was 2.5, and we multiplied that by 1.93 the same way we did height. We came to 4.825. We divided that by 8 as well, and we got 0.6 for the radius derivative. Then we multiply it out. 2 pi times 2.5, which was of course the original radius, if you hadn't remembered, times 0.6 times 5, which concludes to 15 pi. And then we also add to it pi times 6.25 times 1.2, which comes to 7.5 pi. And then I accidentally added pi, our squared height derivative, at the end, which shouldn't exist. By mistake. And then we come to volume of derivative equaling 22.5 pi. And 22.5 pi, of course, equals 70.69, or if you want to round up to 70.7. So the derivative of the volume is 70.7 in the big marshmallow. I'm surprised to admit to you all that the height actually decreases a slightly little bit when it comes to heating up marshmallows in the microwave. The radius, on the other hand, increases pretty rapidly. But if you leave a marshmallow sitting out for a little while, you'll see a small decrease in height. But if you were just to look at it briefly, you would not believe that there was a change in height. But obviously, there is. So in conclusion, our hypothesis that said that the radius would expand and the height would shrink was somewhat accurate.